Hello, everyone. Welcome to today's webinar, Air Quality and the Air-Water Interface of the Chesapeake Bay, organized by Baltimore, Washington, D.C. chapter of Air and Waste Management Association. So before starting this webinar, I'd like to go over some housekeeping items. So please keep your microphone on mute during the presentation, and all questions will be addressed during the Q&A portion right after each presentation is complete. And also we will have, at the end, we'll have combined our Q&A session. Please enter your questions in the chat panel on the right side of your screen, or just save your questions until the end of the presentation. And if you have any comments, please enter those comments in the chat panel. And I have a short poll, the questions that you guys you can answer before we start starting this presentation. Here's one. If you can answer, just pick the response and submit button. Do you all see those polls?
Yes.
Okay. All right. Yeah, now moving. So I'd like to introduce our moderator, David Krask. Dave is the manager of the ambient air monitoring program for the Maryland Department of Environment. He holds a master's degree in chemistry from the University of Maryland and has worked in the air quality field since 1978. In his current capacity, he oversees ambient air monitoring, air quality forecasting, data analysis, and analytical laboratory services. He is also serving as a member of NACAA Monitoring Steering Committee, representing the interest of both MDE and MARAMA member agencies. So Dave, I'm turning to you.
All right, welcome everyone this evening. We're glad you could join us. I think you just moved to the second speaker, Sunhee.
Oh, okay.
All right, our first speaker this evening is Dr. John Sullivan, and John currently works in the Atmospheric Chemistry and Dynamics Laboratory at the NASA Goddard Space Flight Center in Greenbelt, Maryland. He's currently the NASA Tropospheric Ozone LIDAR Network project scientist. His expertise is in performing measurements of atmospheric constituents using active remote sensing techniques such as LIDAR for applications in air quality, satellite validation, and stratospheric trends. Dr. Sullivan has been critical in designing, calibrating, and deploying transportable LIDARs for measuring tropospheric and stratospheric ozone profiles in NASA campaigns such as Discover AQ and Chorus AQ and various NDACC intercomparison campaigns. He was awarded the NASA Postdoctoral Program Fellowship to continue his contribution of novel observations of the atmosphere to further NASA science exploration. In 2017, he was named Early Career Scientist associated with the NASA Science Innovation Fund and supported the ozone water land environmental transition study in the Tidewater, Virginia region. He transitioned to the principal investigator for the 2018 Owlets Field campaign deployment within the northern Chesapeake region. All right, John, we're ready for your presentation.
Great, thank you, Dave. I'm having a little bit of a bandwidth issue, so I'm gonna just keep my camera off for the presentation, but I do see the slides. Can you hear me okay?
Yes.
Yes.
Perfect.
Yes.
Thank you, Dave, for that introduction. It's always great to be with good company. I think I've known Dave for going on 10 years now, going back to my graduate school days at UMBC, and I've known the other two speakers, Joel and Vanessa, for almost just as long. So I appreciate getting us all together here. Essentially, I want to just describe some measurements today that were taken in the Baltimore, Washington, D.C. region in 2018. This is a follow-on study to a 2017 effort that I won't really focus on as much today, but I can certainly give you some references if you want that offline. So there's a long list of collaborators involved in this effort. I've named, I think, some of the primaries here. And at the end of this talk, the slides will be archived, but you can go through and see some of the additional affiliations of some of the other speakers. So really, I think my goal of this talk is just to describe the relevancy of this effort to the sort of air and waste management Baltimore DC chapter, which I don't think should be too hard considering the context, considering the content, but hopefully motivate a little bit of discussion while we sort of prepare for some potential future NASA campaigns. Could you advance the slide, please? So I like opening with this slide because I think it's a nice visual perspective. On the right here is, on the left rather, is a map of Baltimore, including 4 sites that will be sort of heavily focused on during this talk. And on the right is an image taken from the NASA B200, looking down from about 28,000 feet. This image is from Saturday, June 30th, around 3:30 in the afternoon. So if you look at this image and you think about what may cause ozone levels over water to be higher than those over land, there's a lot of things I think in this image that are visually apparent. You obviously see some haze, you see some fair weather cumulus clouds, you see complex coastline. For example, anyone who's been to the Chesapeake Bay watershed area, you probably have experienced wind changes driven largely by temperature gradients. So there's a lot of complex meteorology, chemistry, as well as a really sharp transition in a lot of ways from land to water. So hopefully now the acronym OWLETS is more visually apparent in your mind here, the Ozone Water Land Environmental Transition Study. So really understanding air quality and ozone in complex terrain is the central question that I think this study led out to try to get more observations for. And really the approach was to basically take a suite of measurements to Hart Miller Island, which is shown there in the purple arrow, take a really high resolution, high impact payload to that site, and then try to deploy a similar or have a similar amount of measurements taken at an overland site, which is going to be our UMBC site, and basically try to tease out or infer gradients between the 2 sites within the domain. Next slide, please. So the ozone time series there on the right, I'm hoping you can see it, but really what I want you to just note is I've boxed in an area there that corresponds to June 30th, the same afternoon that picture was taken. And what you're seeing is the Hart Miller Island site, which is the purple color, Downs Park as well, the red color in that time series, are exceeding or nearing 100 parts per billion. This is our 1-minute data from our sort of research monitors. While the continental site, UMBC, the yellow, really maintains a 50 to 60 part per billion concentration during a lot of this time. So very early on, you look at this and you have to start thinking about, you want to understand these differences and their relationships to emissions. And this is a critical step, which we're hoping to continue partnering with maybe folks on this call or folks in the same knowledge area to try to really understand these ozone gradients. I think we as a community we understand tailpipe emissions and how to use them in chemical transport models and how to quantify them in some way with the various emission inventories. But we also need to sort of more fully understand how that leads to formation of ozone, especially in these terrains. And I think that another key component of this is not necessarily understanding ozone at the surface, but in the vertical profile as well. And that's really what I think I'll show you in the next few slides, I think is really important for the area. So next slide, please. NASA has a long history of air quality campaigns. I'm not going to get into all of them, but this was really leveraged the strategy of ALITs from previous campaigns focusing on regional air quality issues. For instance, for additional reference, you can find a write-up that was put together in the October 2020 edition of the EM magazine, where this work was partially highlighted. Next slide, please. So this is a bit of a busy slide. I think that's a good thing because it, in a lot of ways, allows you to sort of visually see how much coordination had to occur to complete this ALITS 2 campaign. So you had NASA and MDE coordinating a lot of measurements, as well as our university counterparts at UMBC and Howard University Beltsville, as well as University of Maryland. So we were able to bring in ozone LiDAR instruments that could measure vertical profiles of ozone, various other AeroNet and Pandora spectrometers to measure column abundances of both aerosols and trace gases, in situ laboratory equipment, as well as measurements on boats on various mobile platforms. And of course, all on the backdrop then of the extensive MDE monitoring network. We were also able to bring in an aircraft. The NASA B200 hosted the Geotazo airborne spectrometer to map below aircraft NO2 columns. So if you want to jump to the next slide, I can describe that a little more in detail with some data. So here we have what we sort of nominally refer to as a raster pattern of NO2 emissions. So you can imagine an aircraft, a high altitude aircraft looking down with a remote sensing payload, and it's able to retrieve that below aircraft column of NO2 and in certain instances, formaldehyde as well as sulfur dioxide. So I'm going to just show or describe some of the view from the aircraft on the same case study day, June 30th, that I'll be describing, and then move to the ground-based perspective. So as I mentioned, the warmer colors here are your higher concentrations of NO2, generally associated with fresh urban emissions. You can see in the morning a fair amount of heterogeneity in the NO2 emissions. You can see throughout the South Baltimore region as well as throughout the southern region there. You can also see some emissions from BWI towards the western portion of this figure. There does appear to be a little bit of speckling of NO2 over the water, which begins you to lead that it's either emissions that have been transported over the water or potentially emissions that are actually coming from various small pleasure craft or small vessels that are in that area. Next slide, please. So maybe I missed it, but the previous slide was roughly 8:30 in the morning was that raster pattern. So now you can sort of visually compare that to the afternoon. 3:30 in the afternoon nominally was the center point for this period. For this raster pattern, and really what you see in the afternoon perspective are much more sort of point source related point sources. So you're starting to see now you're picking out maybe individual spots in the map that are still pumping out a lot of fresh NO2 emissions, and we can work with the state of Maryland to make sure that we understand, what's coming out at these sites. For instance, the hotspot there in the sort of center south is associated with the Brandon Shores power plant. So throughout the day, many of this NO2 can become ozone. I am greatly oversimplifying the chemistry that goes into this, but in a lot of ways, I just want you to understand that although you're not seeing hotspots over the water, it's likely that that is because it's converted from NO2 into ozone, which I'll show you in the next few slides. So go ahead and go to the next slide, please. So this wouldn't be a NASA presentation without trying to link some of this to the satellite perspective. The gridded pattern here is actually nitrogen dioxide columns from the European A&WMA satellite on board the Sentinel-5P. Those are about 7 kilometer square grids there, boxes. So I've overlaid that with the NASA instrument that was flying on the aircraft from the previous slide, and I am very optimistic about these retrievals. I'm very excited to see that the satellite was able to pick out some of these NO2 hotspots in some ways, and some of the elevated concentrations over the water. So one of my other big pushes is to try to get everyone in the community, in the regulatory community especially, to either continue or begin to use satellite data for potential regulatory work. And a lot of that is also driven by NASA's announcement to launch a geostationary air quality satellite called TEMPO, Tropospheric Emissions Monitoring of Pollution. And this is going to be a geostationary air quality satellite that we're expecting to get roughly pictures like this. But if you imagine one of these boxes, it'll actually be 4 pixels in each of these boxes. And it'll be on the order of 1 to 2 hours per retrieval during daylight hours. So we'll really begin to, I think, go into the next sort of dawn of air quality monitoring from space. Next slide, please. So I know we were also deploying VOC grab samples in 3-hour increments to help characterize the air mass throughout the day. I believe Joel may be focusing a little more on this in his slides, so I won't spend a ton of time looking at this, but it is sort of interesting that the colors here indicate the time of day during those grab samples. So you could really spend some time trying to understand, which VOCs we had certain upticks in during times of the day. You can see the 9 to 12 local time hours are generally an uptick in cyclohexane and isopentane. So you can then go back and try to appropriately source those to a specific, VOC emission region. I think it's interesting that you could probably use that to back out, or potentially help to back out, if your emission source is largely from vehicular emissions versus a few other things. So future work, I think, will certainly be to use some of these VOC measurements that are constrained by the ALIT's observations to used in concert with a 1D box model to try to better understand ozone production from them during this day. So next slide, please. So we showed the emissions in the morning from the Geotazo aircraft flights. So you sort of visually now have an idea of where this is all in the same sort of map form factor. You have an idea of where those NO2 hotspots were. So in the afternoon, we're now seeing, this is in situ ozone sampled on the UMD Cessna, roughly 300 to 500 meter sortie. So this is really in the boundary layer, or the marine boundary layer, for most of the time. This is express evidence of these clear gradients in ozone in the overland sites versus the overwater sites associated with that coastal boundary. And this really is supported by those additional surface measurements I showed in some of the earlier slides. This is really a plot that I think I was able to take to my management and basically argue that there are these really quickly changing ozone gradients that we need to continue to explore. So there is currently a graduate student at UMD focusing on these aircraft measurements. However, I do want to urge that a big part of this that we're still lacking is, I think, using these observations to evaluate a really high resolution chemical transport model. We have some high resolution meteorological modeling done during this time during the domain, but we are still looking to work with some teams on chemical modeling. Next slide, please. These gradients were also emphasized and observed with balloon-borne ozone sonde measurements. So we had over 40 ozone sondes, all conditioned in QC/Q8 at UMBC at a single location. So we really have a pretty high confidence level in those measurements. And on the left here, I'm just another example of the gradients that were observed on these days from the overwater site and the overland site. You can see the overland site was more or less 60 parts per billion the whole way up to about 2 kilometers, and overland, the blue and the yellow, I'm sorry, overwater, the blue and the yellow curves significantly higher. I have my expert in training 2-year-old son helping me launch one of the ozone. Well, that's actually one of the radio sondes in this picture. So it was kind of fun. It was a family effort during the summer to get this done. So next slide, please. Thank you. So this slide is a bit busy. I think it's worth just slowing down and describing it a little more, walking you through it. To really further depict the vertical profiles of ozone at the OWLET's super sites, here are LiDAR curtain plots, which is just a time series in the vertical at one location, from NASA's tropospheric ozone LiDAR network. And this is my job at NASA. I'm currently the project scientist for the TollNet network. So this is very near and dear to my heart. It's a network of ozone LiDAR instruments very similar to this throughout the US. We have one Canadian site as well that can be transported into the field to do studies like this. So I've annotated the curtains with a black box. You can also see the ozone sonde profiles as well, just showing, I think, the really nice comparison between the ozone sonde and what the LiDAR we're seeing. But really the left curtain here, as I mentioned, this is the overwater site. It's clear to see that there's a diurnal evolution of ozone pollution that's impacted the water site much more than the continental site. You can really see this when you look over to the right in the continental site, right at about 18 local time or 6 p.m. in that box. You can see it transitions from your yellow colors right to red colors. And that is pretty strong indication of that plume of high ozone that was observed both with the sondes and with the aircraft actually recirculating back over land and impacting the continental sites. At the end of the figure, you can see what appears to be a plume of ozone descending in the surface layer. And we can zoom in and really look at some of this, and we hope to do that in the future. But basically, that has a strong influence on next day ozone. So really what's going on is ozone is on this day in particular being fresh emissions are going out over the water, generally becoming ozone in some capacity, recirculating back, and are then being trapped overnight in some ways, either by deposition or by nocturnal layering. The following morning then, as we know, at least on this case, they can be influential on next day ozone. I should also mention that there's a very different picture of ozone aloft at a kilometer, for instance, in both of these pictures than at the surface. So these LiDARs are also very critical in giving you information above the surface that you wouldn't get with a traditional surface monitoring network. So really, I expect these nocturnal vertical profiles and continuous profiles of ozone continue to be a critical piece of hopefully many state agencies' understanding of the boundary layer pollution, and help to provide a more complete model of basically each state's conceptual model of their air quality. Next slide, please. There were also wind LiDAR and aerosol LiDAR measurements available at several sites during the OWLET's campaign. These have been extremely valuable in understanding the boundary layer heights and flow pattern changes. I will let Dr. Caicedo later on in the third talk probably go into a little more detail on this. But really, we are working with the states and particularly MDE, to use some of the ceilometer network and our own research ceilometer network to provide boundary layer heights, continuous measurements, things like that with some of the PAM sites. Next slide, please. So beyond the measurements described in this talk, there are plenty of other chemical and meteorological observations that were collected to really help improve the quality of ALIT's analyses. Are you guys still there?
Yeah, I'm here, John.
Okay.
We're still here. Lost the slide, though.
Okay.
Sunhee?
Yeah, I'm working on it. Why is it happen? Is it? Guys, see?
We're back.
Okay.
Just give me an extended water break. Thank you. So there's a lot of measurements I don't have time to talk about today, but you know, measurements on research vessels, Pandora, UAV measurements throughout the bay, which are really exceptional, mobile wind lidars, and some small sensors as well. Next slide, please. This is my plug for if you know anyone who's interested in this work, who is a graduate student or internship, summer internship. There are the deadlines, which are rolling, so don't worry about March 1st. It could be next March 1st. Next slide, please. And I just wanted to briefly mention, just for a minute, the ALIT's investigation in some capacity has led me to take a leadership role in a very similar study that's going to be occurring in Houston, Texas in September. You can imagine with everything going on, it's been a rocky road to get there, but we finally have everything in place. So we are going to be doing a similar study in Houston, largely the same sort of, you know, TollNet LiDAR, ozone sonde, Pandora type of effort. This will also be focused more on, in a lot of ways, the socioeconomic discrepancies and their relation to air quality. So this is going to be partially funded by what NASA would deem their applied sciences funding. But really exciting, and this is sort of our next iteration of air quality work. So if you are involved in this or interested in this, or know another state agency that would really greatly benefit from a campaign like this, please try to get in touch with me and we can try to work something out. Last slide, I believe. So really in closing, here's a photo that I was able to dig up from, I think, almost 4 years now, which is the first ALIT Science team meeting, which occurred at MDE. You can probably recognize the tractor there in the background, and you can see TAD as well over on the right. But this was just, I think, a really great way to do a capacity building meeting with MDE as well as NASA and some other agencies and universities. But I think that it really helps to illustrate the collaborative approach of this study. It's not just one agency at the table. It's a lot of other stakeholders and small agencies. And I'm really proud of the whole team, and it's been extremely rewarding to just sort of continue to march forward with ALITs and ALIT analysis. So thank you all. Appreciate it.
All right, thank you, John. That was great presentation. Kevin, do we have any questions in the chat?
No, I don't see any.
Does anyone
wait a
have
second,
any
I'll
questions?
take that back.
Oh.
Well, Susan did ask, was the Edgewood area whited out in the NASA aircraft rosters because of the military base in that area?
Yes. There's a longer answer there, but yeah, Aberdeen Proving Ground is very challenging to fly overhead.
Yeah, that's the only question I have.
Are there any other questions from those in attendance?
There is a question. Any measurement campaigns that include deposition observations?
I do not think we were taking deposition measurements at that time. That's a pretty complicated measurement in some capacity, depending on if you're looking at a specific trace gas, like a flux, for instance. But if the person who wants to reach out to me, I can maybe talk offline about maybe some more of the detail, or maybe we could infer it somehow from some of the measurements we have. But there wasn't a true dedicated sort of deposition in situ sampler or something like that.
I see another question on the chat. Says, can you explain a bit more why ozone was higher over water than land surface?
I could probably spend another hour talking about it. Maybe it's a good segue to Joel. I think he'll probably be hitting harder on this topic, but essentially, you have different cloud coverage. So you have clear skies, so you're able to actually photolyze your NO2 or your emissions more efficiently. So you're getting higher ozone. You have potentially a lower marine boundary layer, so you're not only more efficient at converting it, but you're sort of squishing the box. If you think about the boundary layer as sort of like a classical box, the lid is lower. So in a lot of ways, you are both chemically and meteorologically, it's more it's easier to have ozone, and mixed with this day of just being very stagnant, you sort of had one of the ideal setups for higher ozone over the water that was not over the land. So.
All right. Well, thanks again, John. If anyone has any other questions, we can hold those until the final Q&A session. We'll move on to the next presentation, and the next speaker is Joel Dreesen. Joel Dreesen currently works as a senior meteorologist with the Maryland Department of Environment, where he has been since 2013. Joel obtained a master's degree in atmospheric science with a focus on tornadoes at Texas Tech, utilizing a quickly deployable instrumentation network placed in front of severe storms. Then he garnered operational experience in cloud seeding operations in North Dakota, road weather forecasting in Utah, and he taught environmental science and meteorological courses across the United States and via asynchronous online environment to students around the world. Joel is currently responsible for air quality forecasts for the Maryland, D.C. region, as well as data analysis supporting policy decisions. The Outlets 2 campaign was a long developing conversation and cooperation with Dr. John Sullivan to address air quality forecasting and polity questions, and was built upon 2 pilot ozone seasons of in situ ozone monitoring over the Chesapeake Bay, initiated by Joel and the Maryland Department of the Environment Air Monitoring Group. All right, Joel, take it away.
Thanks for that introduction, Dave. Let me grab the screen. Can you see that?
Yes.
Okay, thank you for confirming that. Yeah, I appreciate the opportunity to talk with everyone today, and it's good to hear from John and Nessa as well. What Dave said there really is the story. When I came to Maryland as an air quality forecaster, immediately the air quality forecast challenges that comes with the Chesapeake Bay and ozone were something I confronted quite often. Now, it's generally going away as the atmosphere gets cleaner, but from both a forecast point of view and a policy point of view, it is still a problem. And knowing that, and then knowing part of my job is trying to figure out what is going on, we started to investigate what we can do to try to take samples on the water but continuously, see if there's a pattern that emerges that at least help with forecasting, and then maybe lead to some policy questions and answers as well. And so that started to happen in 2016 and 2017 when conversations with the Port Authority and DNR led us to Hart Miller Island, and then we were able to conduct measurements over a couple seasons. And then what that did is that really set up the campaign for outlets 2 and let us know what we can expect from some of our days and how best to utilize these high ozone days to get the best kind of sample data set. So here I'd like to focus on what John had mentioned already. The volatile organic compounds were an important part of that. We want to take a look at what they can tell us about where things are coming from. I want to first, of course, mention there's a lot of people that are listed both here and then within the Outlets 2 team as well. I shout out to them and say thanks again for a great campaign, and it's still ongoing to see what it's going to tell us. So John showed these maps already. I want to reiterate here on the top. This is the Outlets 2 domain. The MDE sites here are in red. The ones that are labeled are ones that I call out for either data or for important sites here. Of course, Edgewood is the more or less problem area for ozone attainment. Essex has got a lot of VOC measurements. Old Town has a few, and as does Howard University Beltsville. We also had 2 super sites. So the 2 super sites were here at UMBC and Hart Miller Island. John had already mentioned. And the location of those it works out logistically and fundamentally as well. Those are straddling an area with intense emissions. So not only do we get a land site and a water site, but we're also straddling an area with a lot of ozone precursor emissions. We also added a couple other sites that John mentioned, Downs Park. There's also Tolchester Beach. Tolchester Beach was trying to address whether or not ozone was really getting to the eastern shore or not. Turns out it does sometimes, but not always. So what are we trying to get at with the Outlets 2 campaign as a whole? Well, there are 5 fundamental questions that were driving us. And first of all, the spatial and vertical extent, John showed some of that. What are the mechanisms? Someone actually asked about that in the chat that are creating the ozone over the bay. And then 3 and 5 here are really the meat. How much of that ozone, and then from what source group are those, what source groups are causing that ozone? And then of course there's modeling questions in there as well, but right now I want to focus on what source groups and what locations do policymakers really need to focus on to reduce the ozone that is occurring over the Chesapeake Bay. As I mentioned, there are huge amounts of ozone precursors that are released between UMBC and Hart Miller Island. So on the left here are NOx point sources, and this is these are NOx emissions based on the 2018 permit records at MDE, and then the size of the circle is the annual emissions of NOx. I will tell you on a daily basis, you can get up to 15 tons of NOx just from where I'm circling here, but on average, it's somewhere around 2 to 4 probably. The VOC records are over here, and they're a little bit more dispersed. There's a couple of big circles here. This is actually a brewer, a Guinness brewery right here, and then this is actually a bakery downtown, interesting food-related VOCs. Right here in this cluster that I'm circling, there's a lot of smaller circles, but if I circle this broad area, there's actually about 400 tons a given year additive for VOC. So a lot of VOCs there, and in that transition for moving those precursors into the water, knowing how that fundamentally turns into ozone, we need to understand and take samples over the water. And that's what we want to do with the VOC collection. Part of the photochemistry, of course, is the NOx, but unless we know what's going on with the VOCs, we're not going to get a good idea of the photochemistry. The VOCs are also really great at acting as source tracers. So I'm going to show a little bit of both. The VOC collection was a logistical challenge, to say the least. That you can't take an auto GC out to a water site and install it and have it out there for just a month and then take it back. That's not practical and just not doable. So what we were able to do is take grab samples, but I didn't want to take a grab sample and accidentally get just, for instance, a plume of something going by, or that was too narrow of a window. So what we were able to do is our lab was able to grab a timer that is programmable, and you can get an integrated sample through it. So we programmed 4 VOC canisters for each of our intensive days to cover 4 3-hour windows. And that way we can take a little bit longer of a sample time and see what is through that entire time period, what the concentrations are like. And that's what's pictured here. Now, Katie and Daniel from MDE really did a lot of the heavy lifting, getting the sensors out there, the canisters out there, making sure the sensors were working correctly. They waterproofed them for us, made sure that the integrity was great, and even put like a mesh screen to make sure bugs didn't get sucked up in there. So they really were thinking of everything and made sure that we had some really great viable samples. Now, the location itself, I wanted to show a few different perspectives. These are a few pictures from the archives of the campaign. These are actually the VOCs right here. And so we put them somewhat close to the water, but not too close that we can get a lot of spray. And then, so this is looking east, and then this is looking north from a drone. And then from a boat, the VOCs are actually over here on the left. So they're about 5 meters above the water surface, roughly 5 meters from the edge of the water horizontally. So VOC collection, a 3-hour period, 4 times a day. There was a collection a few days where we only had 1 canister. That was due to logistics. And then there was another day where we actually got a sample overnight to see what was going on during a prolonged episode from like 3 to 6 a.m. But typically it's between 6 a.m. and 6 p.m. where we got our VOC measurements. What did we actually find? Well, in gross concentration, I didn't want to just figure out and see what was actually out by mass. I wanted to know how it compared to other sites. So in the bar graph here, I am comparing concentrations at each of the sites. So Howard University, Old Town, and Essex that we have VOC measurements for. And we don't collect VOCs always. There are 1 in 6 schedule or 1 in 3 schedule. So the 24-hour samples are aggregated over several years at Beltsville and at Essex. But the 3-hour samples at Beltsville and the Essex Auto GC are from the exact same times that we were sampling at Hart Miller Island. So we've got a varied data set here just to really get a vigorous comparison. And there are some individual species that really stand out. As John, I think, already mentioned on some of this, for instance, cyclohexane. The concentration of cyclohexane at Hart Miller Island vastly beyond anything that we saw at any of the other land sites. Also true, for instance, toluene was much higher, pentane, isopentane, hexane. These are a lot of gasoline components. So what do we find? Gasoline, more or less. A lot of gasoline vapors. We also found lots of oxidized VOCs. Now, some of those are from the box modeling done, but some of that is indicated just by the sheer amount of acetone that was out there beyond that. We don't have a lot of other oxidative VOCs that we typically sample for. Acetone can be one of those, and that's an indication, I think, that we've got a lot of oxidative VOCs. Now, that kind of makes sense if you've just got a lot of VOCs compared to the other sites as well. Some of the really reactive VOCs. Now, the table here is the more or less a rehash of the bar graph I showed previously, just showing mean, median, maximum, minimum, and standard deviation for the top 20 compounds. Like we showed on the bar graph, these are ranked by median concentration, but you can see just how much higher, for instance, the gross concentration acetone was than some of the other evaporative compounds. Hexane, isopentane, there's a lot of alkanes that are out there. Then as we move down, you start to get into some global compounds, like chloromethane and difluoromethane, et cetera. Those are longer lived compounds found globally as well, but their presence is actually pretty large. Okay, concentrations aside, which one of those are going to be responsible for ozone generation? Because ozone, ozone from a VOC is going to be also dependent upon how highly reactive it is. So it's not just its concentration, it's a measure of its reactivity. So if you take a look at the maximum incremental reactivity and then compare it to the VOCs, you get a ranking of how much ozone you could form from any one of the VOCs. Now, these are based on the median ozone concentration. So the list here on the left is from Hart-Miller Island. On the right is from the University of Maryland aircraft data. From some of our flight days, just to see a different comparison. You see a lot more potential ozone formation from these in these cans on the island than were in the aircraft. You also see a different set of compounds that are there. For instance, isoprene does not make the top 20 list for Hart-Miller Island. It's way down on the list. So toluene, hexane, isopentane are way up there because their concentrations. Ironically, acetone is not very reactive, but it actually is pretty high up on the list simply because it's got a really high concentration. Okay, that's great. Now we have a picture of the mass that's out there. But let's actually compare the differences between the two sites, Hart-Miller Island and Essex. And I wanted to look at the exact same observation times. So I used the auto GC, the chromatograph at Essex, which is hourly observations, and then bin them so that they were the same as what was at Hart-Miller Island, time-wise, to see which compounds percentage-wise changed or were most significantly different. Cyclohexane was way off the chart. So, but you can see the list here for yourselves. The fact is that the majority of compounds were greater in concentration at Hart-Miller Island than at Essex. And I will put a clause on here. This is during simultaneous observations. So this is using the auto-GC at Essex. Now this is important to note because these two sites obviously represent land and water, but they're also just about 13 kilometers apart. So this is a pretty large disparity in the composition in a very short time period, or a very short spatial period. Of the 32, there were 32 total. Of the 58 compounds were greater at Hart-Miller Island, Essex. The list of 26 that were at least 80% over here on the left. Of that list of 26, that was dominated by C6 to C9 compounds, with 4 of the 5 remaining in C5 compounds. So that's kind of the gasoline range. That not necessarily all from gasoline, but that is the gasoline range. Interestingly enough, there were some compounds that were higher at Essex than at Hart-Miller Island. And a third of those were C9 plus compounds. So now we're thinking, is that diesel? That's a good question. Is there a larger diesel signature at Essex? I think this more or less highlights the importance of episodic variability between these two land and water sites. Because of the observation scheme that we undertook, we can also see how the trend in VOCs was changing throughout the day. And we can get a diurnal variation of VOC concentration, and then also compare it to the NOx concentrations that were there. So first of all, the northern Chesapeake Bay becomes increasingly NOx sensitive through midday, and it's far and above in concentration compared to the other two land sites. Now, what I'm showing here in red is the past observations from Howard University, Beltsville. They're 3-hour canisters from the past 3 years, and then the auto-GC hourly concentrations at Essex. And those concentrations are relatively similar. And then in the green line here, this is the concentration, median diurnal concentration of VOCs at Hart-Miller Island. And the profile is completely opposite. We generally have VOCs go down for numerous reasons, photochemistry and mixing, for instance, at our land sites. Interestingly enough, VOCs are actually peaking right when the boundary layer would normally be increasing over land sites anyway. That results in the ratio, VOC to NOx ratio, increasing and peaking around midday. And I think these go definitely hand in hand. There are more NOx reservoir species. So I'm talking about NOZ, so NOY minus NOx, the reservoir species over the water than at SX, even during episodic events. I think that might make sense if we're talking about just a lot more VOCs present over the water than over the land. You can probably create a lot more reservoir species from that. And that's reflected here in the thin gold line compared to SX. There's just always more NOZ over the water than at the land, over the land site. But there's actually less NOx over the water than at Essex, so over the water at Hart Miller Island, except during specific times and events. And that's where it becomes very important for ozone, is during those specific times and specific events. Okay, what else can you do with the VOCs? There's a source receptor model called the positive matrix factorization. It's built by EPA. And what that does is it tries to apportion the mass of what they're called factors, but they're source profiles of the individual compounds inside those source profiles so that they add up to the total mass measured. What that means is, very simply, is it allows you to profile what your dominant sources are. But what PMF gives you is it gives you VOCs. And for instance, here's what the simple output from the PMF would give you. And then you need to go and interpret what that means. And you can use, for instance, the EPA speciate resource database to interpret what this profile might mean. For the fugitive gasoline profile, what I'm calling here, it's characterized by BTEX, hexane, heptane, and a lot of methylpentanes and methylhexanes. And in all my testing, by the way, this is the largest contributor to VOCs at the island site. And what I realized is, in all my anguish to try and figure out what might be two-stroke, four-stroke, and gross evaporation, the way our sampling scheme worked is that we're pulling in potentially all those sources at once over that 3-hour period. And so they end up getting a little bit mixed. So this fugitive gasoline really applies to probably two-stroke, four-stroke, and total gross evaporative gas, just simply due to the evaporation scheme, right? Two-stroke, you're probably spitting out gasoline from the exhaust anyway, so you probably be very close to what a gross evaporative gasoline might look like from like a storage tank, for instance. Then we get into some other interesting profiles. I threw the trace gases into this as well, not just the VOCs. And what came out was a profile that accounted for about 74% of the signal for NOx measured at the island. So the trace gas measurements were also binned into 3-hour averages to match the VOC measurement periods. And in this profile, also, there's some other compounds that could probably distinguish where it's coming from. For instance, chloroform, ethanol, the light alkanes and alkenes. So maybe talking about some natural gas, perhaps. SO2 was also very high here. And I'll show you why I'm also calling this Southern Baltimore in a second. Now, I decided on 5. This has been really giving me heartburn on how many profiles, because there are the user decides how many profiles might be there. And I've tested everything from 5 to 10. And right now I've decided on 5. Let me come back to the 1-pentene state. Diesel does come up. It accounts for a very small amount of the total methane, total non-methane hydrocarbons. And that makes sense, right? The diesel is not very volatile. There's also a distinguished gasoline permeation losses. So this is different than the gross gasoline. And no matter what test you throw at this or a different variation, this is a very strong signal. The permeation losses that are defined by the EPA speciate model are things like gasoline coming from a carburetor or the headspace of a tank, or maybe a seal on a gas line not quite being right. Lastly, I'll come back to this 1-pentene. Why is there a reactive compound? 1-pentene is pretty reactive as an alkene that is always there, but it's was weakly correlated to everything else, and it was actually anti-correlated to combustion tracers. So NO2, CO, CO2, it was actually anti-correlated to those. And yet this is a pretty distinct factor. It's kind of this background state. And so right now I'm calling it the marine biogenic factor. And I can come back to that and talk about it later. But what's great about the PMF model is that it applies a concentration weight to each of the samples. And since each of these samples is associated with a date and time, you can then associate that date and time and the sample with a trajectory. So what I've done in this case is I've associated all 34 canisters with a trajectory, but weighted the trajectory by the maximum concentration contribution for each of these factors. What it essentially means is where are these sources coming from? In a nutshell, that's what that means. So for instance, why is Southern Baltimore called that factor? Why am I calling it that? Well, because all the trajectories in that factor are really heavily weighted right back towards Baltimore. SO2, the light alkanes, the chloroform, remember, the fugitive gasoline, on the other hand, is coming from no really preferred source, which probably means it's an area source. The diesel, you see that the trajectories are aligned more or less with the bay, so that's a great thing to see there. And gasoline permeation losses, we're looking at trajectories that are, again, mostly coming from the bay. And the thought here is that this is boats, because if the trajectories are all coming from the bay and they're talking about more or less headspace losses, things like losing gasoline out of a gas line, things like that. There's a lot of recreational boats that are just camped out here all along this coast. The 1-pentene factor, again, is more or less like an area factor, but perhaps you could say there's a signal that's coming from the bay. I'm not completely confident on it, but it's always showing up in the tests. So a great thing to see. By the way, the meteorology driving this was the HER. And then what we can do with that further is we can look at these 34 canisters and apply them to individual events to know what might have been causing an ozone event or non-ozone event for that matter. And I want to focus on a few canisters here. Here's June 17th. This is an ozone exceedance at Hart Miller Island. And the black line here represents the diesel factor. These two dots are the second and the fourth highest diesel factors for the entire campaign, and they both show up on the same day, meaning that there was a diesel influence, a strong diesel influence on June 17th. Ironically, there was 2 times as many what I'm calling hoteling hours, I mean boat at the port, just prior to this period. Also note that there's the largest fugitive gasoline contribution on this day, on June 17th. It's boats, and you can look at the minute data observations, and you can tell that there's a lot of boats out there. And it's Father's Day, for those of you who don't remember. Same thing, I would go to June 29th, the quintessential Bay Breeze Day. There's that 1-pentene influence actually shows up. So is there a natural factor here that's showing up? Great question. One last point to note is the Baltimore factor is strongest in the morning and then fades away. And that makes sense, right? Because if it's dominated by NOx, the photochemistry would actually get rid of the NOx through the day. And you'd end up with a lesser signal later on in the day. And note, John was talking about June 30th. June 30th had one of the strongest Southern Baltimore influences of the campaign. All right, so summary, gasoline compounds were the dominant VOC source for mass at Hart Miller Island, and the disparity between Hart Miller Island and Essex. And I remember that's over a very short difference. And I think that results in reservoir species being greater over the water. So any NOx that's there, if you don't make the ozone, you can certainly make the reservoir species. A little bit of speculation there. Hopefully modeling would back that up. Logistical constraints, just because of getting those canisters out to the island. There's some inability to separate some of the sources because they're probably all in the canister together. But we were still able to identify recreational boats, diesel influences, Baltimore influence, and maybe that marine biogenic influence. And this is more of a question now, is while recreational boats are strongly influential on VOCs, based on this analysis, their ability to create ozone events may be curbed somewhat by the imbalance of NOx. And that's because the NOx is much more water soluble. And since a lot of those boats mix the exhaust with the water, you might actually take out some of the NOx and be left with just the VOCs. Lastly, that might be what causes the larger NOx variability to be explained from Baltimore rather than the marine locations. For instance, the marine boats out there may not explain the NOx variability from what I just explained with the exhaust, for instance. The exception might be the hoteling diesels, which could be involved also with that Baltimore factor. So thank you. I'll just leave with this question, this picture from Shinrong. I took from, I believe this was June 17th. You could actually see boats on the bay on that day. Thank you.
Thanks, Joel. That was an incredible amount of information that you packed in there. I'm sure it's going to take people a little while to digest that. Kevin, do we have any questions in the chat?
I don't see any in the chat right now.
Okay. Are there any questions from the attendees?
Dave, there is a question in the chat now. It's any thoughts on VOC sources contributing from the eastern shore?
Good question. You could get, I suppose, an agricultural influence, a pesticide application, perhaps. Nothing popped up in the analysis. There were some toxics that showed up, but their concentrations were completely tied to trajectories going back to Baltimore. So nothing really conclusive showed up from the eastern shore. For VOCs.
That's all in the chats right now, Dave.
Okay. Any other questions from that people want to speak up on? All right, then. Well, if you think of some, I know that was a lot of information to digest. You could just do that at the end of our third presentation. Okay, let's go on to the third presentation then. Our next speaker is Dr. Vanessa Caicedo, and she obtained her PhD in atmospheric sciences from the University of Houston, where her research was based upon the retrieval of the planetary boundary height, coastal boundary layer evolution and climatology, and the evaluation of observed and simulated boundary layer dynamics in herbal coastal environments using remote sensing methods. Dr. Caicedo is currently a research scientist with the Atmospheric LIDAR Group at UMBC JSET, and her work includes boundary layer meteorology, air quality, atmospheric chemistry, and boundary layer height retrieval methodologies. Welcome, Vanessa, and you can proceed with your presentation.
Thanks, Dave. Let me see if I can get this working again. Is that showing up for everybody?
Yes.
Great. I will be taking a little bit of a closer look at some case studies, looking at observations of bay breeze events over a marine site, which you guys have heard about many times now, Hart Miller Island. So before I get into that, though, I do want to acknowledge all my co-authors here who have really contributing to putting this this together. It's going to be a paper hopefully submitted within the next month or so. So as I mentioned, I'll be looking at two very specific days during the ALITS 2 campaign. So these are June 29th and June 30th. And as we heard about before, we knew that we were looking at horizontal gradients of ozone and pollutants over over the area, but I kind of wanted to focus on the vertical distribution of pollutants. So these 2 days presented really strong and clear Bay Breeze conditions with also some elevated ozone. And so using that data specifically located at Hart Miller Island, and we can kind of see those maps, and you have seen many of those maps already. We are using a Doppler wind lidar. It's a scanning lidar to hopefully give us some indications of the dynamics over the bay. We're looking at surface meteorology and chemistry at that site as well. We had twice a day, I should say ozone sons, although I'm using really the radiosonde part here. We had the NASA Langley mobile ozone lidar, which you saw some previous grabs from that as well in John's presentation. And ultimately the University of Maryland research aircraft. And so you'll notice here that we're looking at those spirals that are kind of displayed here in the graph, and these were subset to just those that reached the lowest altitudes and remained over the water. So again, a little bit really taking a look into the Bay Breeze dynamics. So just a little bit of background for these 2 days. We had a high pressure system that was slowly making its way towards us on the East Coast. It's a little bit hard to see, but we're around where that green star is. And so June 29th kind of starts with that high pressure system more to the west of us, and then slowly makes its way kind of over us. And high pressure systems are typically associated with just the ideal conditions for pollutant accumulation. So we talked about that a little bit before. So high temperatures, clear skies, and calm winds. So the first thing we did was look at data from the wind lidar. So really looking at that Bay Breeze dynamics over the water. Now, this lidar is a scanning lidar, so you'll see quite a bit of different types of data coming from it, but this is just the overall wind speeds and directions. So for these 2 days, we're looking at the beginning of the day, starting off with consistent vertically offshore flow throughout what we're measuring here. But we do see that for June 29th, we had a stronger offshore flow than that kind of below here in June 30th. We also see that the onset of the Bay Breeze, so that shift towards onshore flow, it's a little bit hard to see, but we'll be able to see it better in other graphs, happened about 10 local time on June 29th, and much earlier, around 7 in the onset of on June 30th, I'm sorry. And what was really interesting to see is that we typically are very easily able to recognize these Bay Breeze events because they create kind of a convergence zone between onshore and offshore flow, and then that offshore flow gets lofted up above the Bay Breeze over the water. And so that's what we're seeing here. Above the onshore flow, kind of in these lower altitudes, we do see that return flow of the offshore flow, but more specifically, that offshore flow does slow down when we are able to develop a Bay Breeze. But for June 29th, it pretty quickly gets pretty strong again, or relatively strong, I should say. But for June 30th, it kind of does remain pretty weakly above the Bay Breeze. So now looking at more wind lidar data, these are just conical scans at a specific angle. So really this lidar is right at the edge of HMI, and it just scans all around 360 degrees. And it's able to kind of tell us just where is the flow coming from. So we use these specific scans to really begin to determine the vertical extent of these flows. So as I mentioned, during these types of Bay Breeze, we get some near surface onshore flow from the Bay Breeze, and above we get that offshore flow. So we define the Bay Breeze height as that transition between those two flows. And what was interesting about that is whenever we compare that to the thermodynamic or potential temperature from the radiosondes, we're finding that that Bay Breeze height really does correspond to what we would call the mixing layer height. So you'll see here a progression of those scans. These are not all the ones we have, but just a selection how you can see kind of that change from offshore flow here coming from northwest and eventually making it coming from the southerly direction, and the same thing for June 30th. We're also able to see a little bit of the horizontal development, especially on the 30th, where it was a much lower and gradual development of the Bay Breeze. So we start with pretty calm winds, kind of those white zero colors, then turning into more of this green, especially here at the edge, and that kind of green color actually getting bigger and bigger until it actually overpowers the range of the LiDAR, and we're just seeing constant southerly flow. Let's see. So now looking a little bit more into vertical motion. So with this LiDAR, if we point it straight up, it's able to tell us a little bit more of vertical motion right above the LiDAR sight. So for these two graphs, you'll see that red is indicative of upwards motion, while blue is downwards. And if you remember from the previous slide, we did derive some sort of Bay Breeze height, or I may call it mixing layer height interchangeably. And so that is just superimposed on top. Those two little dots are just the radiosonde derived mixing layer heights to kind of tell us where we are. And so what we're seeing with these 2 days is that although they are both having a Bay Breeze onset, they are significantly different. So for both of them, though, you do see that the offshore flow, especially above the onset of the Bay Breeze, is increased. So the vertical motion from this is increased, and that typically is indicating that we're getting some sort of land-generated thermals that are getting advected offshore with a return flow here. So we see that in those 2 days. On June 29th, we see kind of more of a textbook development of vertical flows in relations to the Bay Breeze. We get an initial increase in vertical velocities right before we're able to detect a Bay Breeze, and that's just what we call the Bay Breeze front. And we see decreased vertical motion within the Bay Breeze flow. So just under that black line, we do see significant decrease in that vertical motion. And again, that's not surprisingly, just because the Bay Breeze is going to be a largely horizontal motion. But for June 30th, we kind of see the opposite. We do not see any sort of increase in vertical intensities at the beginning of the Bay Breeze. But most importantly, we're seeing actually increase in upwards motion kind of after around 14 local standard time and continuing on. And if we relate that to that Bay Breeze height, we can see how an increase in upwards vertical motion could result in this kind of higher Bay Breeze height than that of the previous day. Now we can also look at the vertical variance of these measurements, and that is to help us characterize a little bit more of turbulent intensity. And so again, not surprisingly, the thermals getting advected from the offshore flow over the water are the ones that contain most of that turbulent intensity above that Bay Breeze height here for June 29th. We also see some kind of highlighted of intensity right at the border of that Bay Breeze height on June 29th, and we'll talk a little bit more about that later. And for June 30th, we did mention before it's a weaker offshore flow, so then we also see a slightly weaker turbulent intensities on that offshore flow. Now, the goal of this was really trying to understand the Bay Breeze dynamics and see if that could help us understand a little bit more of how that may be impacting the vertical distribution. So now we're kind of going back and seeing a little bit of those ozone LiDAR profiles. So here is June 29th. And for June 29th, we see that most of that ozone is really kind of capped below that Bay Breeze height, which is what we're expecting to see. And I'll just mention here, these markers on the bottom are surface ozone measurements. And the ones here on the right are ozone measurements from the aircraft. And so continuing on to look at this day, we see that above that Bay Breeze flow, so on the return flow, we do see a little bit of higher ozone. I think we averaged it to daytime concentrations of about 64 ppb. that were likely just advected from inland sources through that return flow above the Bay Breeze. Around 16 to 18 UTC, we see that the ozone is pretty well mixed through the surface through the Bay Breeze height. But we also see that corresponds to the highest surface ozone at the time where we're actually seeing a decrease in the Bay Breeze height. So could that be an indication of just a factor contributing to the high ozone? So if we start reducing that volume, kind of closing that box, as John mentioned earlier, could we be enhancing our surface concentrations at this time? And that turbulent intensity that we kind of saw before was something that we thought, well, we've always wondered about any sort of entrainment between flows. In this case, in onshore and offshore flow. In other cases, we may wonder about residual air reservoirs. And so it was interesting to see that at this boundary, we are seeing some sort of intensified turbulence. And so that was kind of a question that was brought up. Could this be an indication of flux between flows? For June 30th, we do overall just have higher ozone concentration, especially when we look at the surface measurements. Sorry about that. And that kind of comes back from what we know about Bay Breezes. When we tend to have consecutive Bay Breeze days, we tend to just recycle and recirculate air masses. So here that could be explaining that a little bit. But again, just a little bit of a theory of what we've seen in previous cases before. The highest surface ozone happened from around 11 to 14 local standard time. And that is the time where we see kind of the Bay Breeze staying well below 600 meters. After around 14 local time, we'd start to see a decrease in the surface concentrations of ozone. But we are actually seeing that increase in upwards vertical motion from the previous LiDAR observations. So it kind of helped us maybe explain a little bit of the vertical distribution in this day, right? If we have constant upwards motion or just increased upwards motion, that could be preventing those ozone concentrations to be kept really lofted above the surface, as we see in this image on the bottom. The area of the highest ozone is kind of also right at that boundary of the Bay Breeze height. So that was another indication of could we also at these times be seeing some sort of entrainment? Could that contribute to any pollutant concentrations within that Bay Breeze flow, as is indicated by that a little bit of slight enhancement in the variance? And I think that's it. Yes. So conclusions quickly. We're finding that really the intensity of the offshore flow before, during, and after the Bay Breeze development plays really an important role. So again, depending on the strength of the offshore flow, that will determine the timing. So a stronger opposing flow is not going to allow for that Bay Breeze to develop maybe as deeply or as quickly. The interesting part was, which I was excited about, was this upwards vertical motions that were enhanced on June 30th. That kind of could really start to explain why we're starting to see a decrease in surface ocean, especially at the time that we're expecting peak ozone photochemistry. And kind of maybe keeping those ozone values lofted above the surface. Higher ozone concentrations were measured during times where we saw relatively low or decreasing mixing layer height or Bay Breeze heights. So that was kind of an important indication here as well, that we cannot forget the meteorology. And all of that is to say that this was a very meteorology and dynamic focused study, so we cannot neglect any sources or chemistry behind any of these concentrations to really get the entire picture. So with that, thank you. I'll take any questions if there are any.
Thank you, Vanessa. That was a really interesting presentation, and I don't think I've quite seen some of those illustrations, the graphs you produced before, especially the conical representations. Those are very fascinating, and I'm sure there's a lot of great information that can be gleaned from those. I think, Kevin, we do have a few speakers from the, questions from the chat.
Yeah. One question is, when you talk about the inland sources, slide 7, do you mean from the mainland?
I'm wondering if that question is to Joel. I cannot pinpoint a real source. Again, I can only see what's arriving at the site. So to actually say this is exactly coming from inline or the specific source, I'm not able to really say that.
Okay. All right. So we got a long question here, maybe a couple of questions really. I'd like to hear from the speakers their thoughts about the role of NOx scavenging in the bay. It would help to see that same graphic over the bay from the first speaker, but showing modeled concentrations of ozone versus modeled concentrations of NOx. What is the dynamics of NOx transport into the bay? Yeah, I don't know. I can keep reading on. There's quite a number of questions, so it's actually for all of the speakers. So, I don't know. You want? I'll continue with it, and then I guess the speakers can individually look and see if they give more specific answers. The rest of the question is, if there is excess NOx in the bay, i.e. excess beyond that consumed in forming ozone from VOCs, wouldn't NOx scavenge the ozone over the water, and ozone concentrations would be less than what is observed? Or are the higher ozone concentrations over the bay a product of weaker vertical distributions as suggested by the third speaker? So that question is for all three of you. So I don't know. Can the three of you see that comment? That's the question.
Yeah, I can see the question. I'll start this off. One thing that I've always had problems with is the idea of just classifying the ozone problem over water just due to mixing. That's certainly part of the issue, but the mixing works both ways. If you don't have if you don't emit the pollutants or get the pollutants into the shallow, stable layer, then you're not going to get the ozone in there either, right? So it would stay above that. So either something has to be entraining into that surface layer or be emitting in that surface layer. So there's two things that could be going on to address that question is, are we talking about sources that are emitting on the surface of the bay, or are we talking about sources that are being pulled into the bay? And I think both can occur. Based on what I've seen, the sources that are probably on the surface of the bay are mostly going to be VOC dominant, and that you get these large mixing events from the mainland or from Baltimore in this case, when you get a larger NOx surge that could be put down into the bay. And then the following day, if you've got a lot of NOx reservoir species, you're going to kick off ozone that next day right away because you've already got it in the surface layer. That's kind of my quick take on that.
Do any of the other speakers want to comment?
Yeah, hey Joel, that was this is John, the first speaker. I think Joel laid that out really nicely. I think that there's also the perspective of sort of the micro conversion of NOx to ozone and sort of the macro scale. And you know, with such high abundant levels of sunshine, you're going to have a lot of conversion from NOx into ozone, possibly other pathways as well. So, you know, in a classical sense, you would expect the NOx to help titrate out, especially sort of in your lower sun levels, like in your sunrise and sunset. But you get a lot of layering in near the bay. And it can really be, it really helps to stratify some of those lower levels in the atmosphere. So we've seen situations where we have a 100-meter layer, a temperature inversion at 100 meters that might trap your surface pollutants, but then you might have some ozone aloft above that carried over from the night before. So it's really trying to understand some of that in high resolution, and especially getting a better picture of that nocturnal residual layer and the mixing down, especially in the morning hours. So it's certainly a complicated piece to the whole puzzle, and I think Vanessa's wind measurements actually really help highlight some of the complexity in time, temporal and vertical.
Vanessa, did you want to add anything?
I think these guys did a great job. You know, I don't know if it's a one answer versus the other. I think, you know, the complexity in the chemistry, in the transport, and in just the meteorology are going to make it difficult to just pinpoint to one. But we do see how that interaction can have a big impact. So I think that would be all that. I think we really need to bring all of it together and start maybe seeing what has the biggest impact and start kind of putting it in order that way.
So Vanessa and I were talking before everything got started, and I was really excited to see her slides because it's something that's been missing from my explanation. I've had this long-standing hypothesis, but if her analysis is implying that there was mixing during that event, then I can pretty solidly say now, based on the trace gases and the VOCs that hit the island, that we can trace it back to Baltimore, because the trajectories do that. And there's traces of SO2, there's a CO2 surge. There's actually, if you go into the really high resolution detail, there is a methane surge that corresponds very well with a signature that you would get from a landfill. And there's a huge landfill right next to the power plant. And for a while, I actually thought it was one thing, but if you look really closely, they're only about 5 minutes apart in the data. And it's almost like a slam dunk. If Vanessa's data is saying that, then we can say that, yes, we've just taken this aloft reservoir of pollution that came from Baltimore, slammed it to the surface, and then pushed it towards Hart Miller Island. And hopefully hopefully Vanessa and I can work together to make that puzzle piece come together.
Okay, Dave. Well, actually, I was going to say there are no more, but there is one. Could Dr. Quesodo go over her conical view slide again and explain the different views? What times? How does she define bay breeze versus offshore? Is it with reference to HMI itself?
Yes. Let me get that going again. Oh, great. So yes. So here, I'll use these kind of bottom examples just because they're easier. So anything in the directions kind of perpendicular to this edge of HMI are considered to be onshore flow. We also added a few more degrees of leeway just to kind of account for the, in Baltimore shoreline. And so that I can kind of detail a little bit more, and we have that in the paper. But basically, the way that it's calculated is, especially we look at these kind of G, H, and I graphs here, we can see how there is this blue colors, which is flow towards the lidar. So that kind of coming in towards the lidar, which is here at the center. And then the flow kind of after that green is flow away from the lidar. So it's just kind of a little blob of just developing wind flows that are coming from a southerly direction into HMI. So then you can see kind of that projection here. Now these scans are just at a single elevation. So the beam of the lidar will not be just pointing straight horizontally, but we do use different elevation angles. So for this one, after the measurements in maybe letter I, we don't see that transition anymore. But with the higher elevation angles, let's say 50 degrees or 75 degrees, we are able to still see those two flows vertically. And so then we can kind of keep finding that transition height. And whenever I kind of showed those results, you'll also see it with a plus or minus, and that is just, we do these scans pretty frequently, so there's a lot of them, and then we average those heights into what I displayed here.
Okay, thanks. There is one final question here, it looks like, and that is, Hannah asked, what are the next steps for each of you for your research?
I like to work with Vanessa more on the meteorology piece of this and connecting it to the surface obs and VOCs.
Yeah, I would say, as I mentioned in my talk, that what's one thing that's needed in this study is a sort of a high resolution chemical transport model run. And we have, I guess this is a primer for anyone who may know someone interested in doing this, but we have a pretty high resolution 1 kilometer WRF meteorological run that would be great to maybe do some offline chemistry with to try to better understand this. But one of the goals in the study that actually got it funded was also some model evaluation and in particular forecast evaluation. And it just has been really tough to find folks with the bandwidth to help us out with that. So that's sort of where I'm headed next. Hopefully find someone, maybe a grad student.
Yeah, I'll just mention, so hopefully we'll get this this study published, and I'm really excited for future campaigns that are really focusing on these coastal areas. So I know, as just John mentioned, tracers is going to be really exciting. A lot of measurements, more probably than what you've seen here, particularly in the meteorology side, which is what I've been kind of focusing on. So I think that would be our next steps, getting more involved into that.
Okay, Dave, I don't see anything more in the chat box.
All right, well, I'd like to thank the speakers. Those were all really great presentations, very interesting. I do see the opportunities for lots of good follow-up work, and I hope Joel does get to work closer with Dr. Casado here, and I think that'll be very productive. Sunhee, do you want to wrap things up?
Yes, so thank you. Thank you for the Dave and our 3 speakers, and also Kevin to monitoring the questions. I'd like to move over to our upcoming event. The BW chapter is currently planning a social trivia event, tentatively scheduled on April 22nd. The detail will be sent out shortly. So stay tuned for more events to come and join our LinkedIn group. And if you are not our A&WMA member, please consider joining. The A&WMA is planning, they are providing various webinars, conferences, or workshops throughout year. So please check our upcoming events on A&WMA website. And there will be a A&WMA annual conference exhibit, which is on 114th, on June 14th through June 17th. So you can find the information from A&WMA website, awma.org. And
that's going to be a virtual conference.
Yes, thanks, brilliant. So you have any questions about our chapters, please feel free to check out our chapter website and contact us at our chapter email address provided here. And I'd like to have the last poll question to go out. Please submit your answer. It'll be out there. And as I said, if you have any comments, please leave your comments on the chat. Thank you.